Hi, I'm Alex. Tonight we're exploring a strange fact about astronomy. The universe is measured using a distance almost no star actually sits at. It's called the parsec. It's not a natural boundary, it's not based on light time or physical limits, but on a tiny angle measured from Earth. So, why does this one abstract distance still define how we map the entire cosmos? And if journeys like this resonate with you, a soft like or subscribe helps keep these stories alive. Let's begin. For most of human history, stellar distances were a complete mystery. Ancient Greek astronomer Hipparchus, working around 130 BCE, cataloged over 1,000 stars. He measured their positions, carefully tracked their movements across the sky, and recorded their brightness with remarkable precision. But distance he had absolutely no idea. His best guess was that they sat on a crystal sphere, beyond the planets, all equally far from Earth. This wasn't stupidity or lack of imagination, it was the best explanation fitting the available observations. The stars appeared to be fixed points of light that never moved relative to each other. They kept perfect formation, night after night, year after year, century after century. The ancient Greeks had no instruments capable of detecting what we now call stellar parallax or proper motion. The stars really did appear absolutely fixed. Every observation confirmed their model. The ancient Greeks actually had a word for this celestial sphere. They called it the firmament, from the Latin word meaning to make firm or strengthen. The idea was that the stars were literally embedded in a solid crystalline sphere that rotated around Earth once per day. This sphere sat beyond the planets, which the Greeks knew moved against the stellar background. They had tracked Mars, Jupiter, and Saturn carefully and watched these wandering stars trace complex paths through the constellations. But the stars themselves never budged relative to each other. Aristotle, writing in the 4th century BCE, argued that this celestial sphere must be made of a fifth element, different from the earth, water, air, and fire found below the moon. He called it ether, or quintessence. This substance was perfect, unchanging, and eternal. The stars embedded in this sphere partook of its perfection. They never changed. Brightness never appeared or disappeared, never moved, except for their daily rotation with the sphere itself. This model made sense for 2,000 years because nobody had instruments capable of detecting stellar parallax or proper motion. The stars really did appear absolutely fixed. Imagine you are Hipparchus on a clear night with no light pollution. You look up and see thousands of points of light completely fixed in their positions. Only 5 wandering stars, what we now call planets, move through the background of stars. Mars, Jupiter, and Saturn trace complex loops through the constellations over months and years. But the stars, they never move relative to each other. Not by the tiniest amount you can detect. The constellation patterns remain identical. Orion's belt looks the same tonight as it did last year, 10 years ago, 100 years ago. As far as anyone can tell, it looked the same to your grandfather and his grandfather before him. This wasn't lazy observation. The Greeks were meticulous. They measured angles between stars to fractions of a degree using careful sighting instruments. They tracked positions over decades, and they found zero change in the stellar patterns. Zero. This wasn't stupidity. It was good science, the best possible, with the data available. When every observation confirms a theory, When no contradictory evidence exists, when the model explains everything, you see you accept that model. That's how science works. The Greeks had no instruments sensitive enough to detect stellar parallax, the tiny apparent shift in a star's position as Earth moves around the Sun. They had no telescopes to magnify distant objects. They had no way to measure the incredibly small, proper motions of nearby stars moving through space. The firmament theory wasn't a failure of imagination. It was a rational conclusion from excellent observations. The stars appeared fixed. Therefore, they probably were fixed attached to something rotating around Earth. When Ptolemy compiled his great star catalog around 150 CE, documenting over 1,000 stars and their positions, he found the same patterns Hipparchus had seen 3 centuries earlier. The constellations hadn't changed shape at all, not by any measurable amount. This was powerful confirmation. 300 years is a long time. If stars were moving through space, if they were scattered at different distances, like ships on an ocean, surely some change would be visible over 3 centuries. But there was none. The crystal sphere model was reinforced. For 2 millennia, nobody did better. The technology simply didn't exist to detect the tiny motions and shifts that would reveal the truth about stellar distances. Generations of astronomers accepted the firmament because it fit all available evidence. But everything was about to change. In the 17th century, a new invention would revolutionize astronomy and begin the long journey toward measuring stellar distances. Telescopes were coming, and with them, new questions that would challenge 2,000 years of accepted wisdom. The crystal sphere was about to crack. Telescopes were eventually invented in the 1600s, and they revealed astonishing details about the moon planets and stars. Galileo saw mountains on the moon and 4 moons orbiting Jupiter. He discovered that the Milky Way consisted of countless individual stars, not a fuzzy band of light as it appeared to the naked eye. But he still couldn't answer the fundamental question of how far away anything was. The stars appeared absolutely fixed. If something doesn't move, you can't triangulate its distance. You need to view an object from 2 different positions and measure how its position changes. That's how your brain perceives depth. Your 2 eyes see slightly different views of the world, and your brain uses that difference to judge distance. Close one eye and reach out to touch something. It's harder, isn't it? You've lost that depth perception. Your brain needs the parallax between your 2 eyes to accurately judge how far away things are. For stars, we needed something similar, but on a cosmic scale. Human eyes are separated by only about 6 centimeters. That's enough to give depth perception for objects a few meters away, but utterly useless for anything at astronomical distances. We needed a much larger baseline. By the 1600s, scientists had figured out a clever idea. Use Earth's orbit around the Sun as your triangulation baseline. Johannes Kepler had established that Earth orbits the Sun in a roughly circular path. By the mid-1600s, astronomers had measured Earth's orbital size fairly accurately by observing transits of Venus across the Sun's face. They knew Earth orbits in a path about 300 million kilometers in diameter. That's 186 million miles. This means that in January, Earth is on one side of the Sun, And 6 months later, in July, Earth is on the complete opposite side. The plan was elegant. Observe a star in January. Note its exact position against the background of more distant stars. Then observe the same star in July from the opposite side of the orbit. You're viewing from two positions separated by that full diameter. It's like having eyes separated by 300 million kilometers instead of 6 centimeters. Even the nearest stars should show a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, use basic trigonometry, and you can calculate the distance. The concept is beautifully simple. Draw a triangle. The base is Earth's orbit diameter. The vertex is the star. Measure the angle at the star, and you can calculate how far away it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The problem was that the shift is incredibly tiny. We're talking about angles smaller than 1 arcsecond. To understand how small 1 arcsecond is, imagine dividing a degree into 60 parts. Each part is 1 arc minute. Now divide each arc minute into 60 more parts. Each of those is 1 arcsecond. So 1 arcsecond is 1/3600th of a degree. To give you a physical sense of this, if you hold a tennis ball at the distance of 1 kilometer, the ball appears about 1 arcsecond wide. If you're standing on a beach and you see a ship on the horizon 10 kilometers away, a person standing on that ship's deck appears about 1 arcsecond tall. That's the kind of precision 17th century telescopes would need to detect stellar parallax. They couldn't do it. The best telescopes of the time had mechanical wobbles, larger than the signal astronomers were trying to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature changes made telescope parts expand and contract by amounts that threw off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature. Wind pushed on telescope tubes. Every possible source of error was larger than the signal being measured. Robert Hooke tried in 1669. He was a brilliant scientist, one of England's leading experimentalists. Hooke had contributed to optics, mechanics astronomy, and biology. He coined the word cell after seeing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist tackling a serious problem. Hooke built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was that mounting the telescope high up would put it above some of the turbulent air near the ground. He observed a bright star called Gamma Draconis. For months, took careful measurements and detected what he thought was a shift in position. He published his findings, claiming to have measured stellar parallax at last. He was wrong. What he had actually detected was something called stellar aberration, a different effect entirely that comes from the combination of light's finite speed and Earth's motion through space. Here's how aberration works. Light travels at finite speed about 300,000 kilometers per second. Earth is moving around the sun at about 30 kilometers per second. When you point a telescope at a star, you have to tilt it slightly in the direction of Earth's motion to compensate for the fact that light is traveling down the tube while Earth is moving sideways. It's like running through rain. Even if the rain is falling straight down, you have to tilt your umbrella forward because you're moving horizontally. The rain appears to come at an angle because of your motion, even though it's actually falling vertically. This aberration effect is real and measurable. But it's not parallax. Parallax makes nearby stars shift against distant background stars. The nearby star appears to move in a small ellipse over the course of a year, while distant stars remain fixed. Aberration makes all stars shift in the same direction by the same amount regardless of distance. Hooke had discovered something real and interesting, just not what he thought he'd discovered. The actual discovery of aberration is credited to James Bradley in 1728, who figured out what was really happening and explained the physics correctly. Parallax remained elusive. William Herschel tried a different approach. Herschel was the astronomer who discovered Uranus in 1781, the first planet discovered in recorded history. Before Uranus, humanity knew 5 planets, Mercury through Saturn, all visible to the naked eye and known since ancient times. Herschel's discovery of a 6th planet made him instantly famous. He reasoned that if you observe double stars, pairs of stars that appear close together in the sky, one star in the pair might be much nearer to Earth than its companion. If so, the near star should show parallax, while the distant one doesn't. Over many years, he made thousands of painstaking measurements of double star systems, carefully tracking the angular separation between the components of each pair. He never found parallax, but his work wasn't wasted. He discovered that many double stars aren't just chance alignments, 2 unrelated stars that happen to lie along the same line of sight from Earth. They actually orbit each other gravitationally. He had discovered binary star systems, pairs of stars, bound together by gravity orbiting their common center of mass. This turned out to be one of astronomy's most important discoveries. Binary stars became crucial tools for measuring stellar masses. By watching how fast 2 stars orbit each other and measuring their separation, you can calculate their masses using Newton's laws. This is still how we measure most stellar masses today. Herschel's failed attempt to find parallax led to a discovery that transformed stellar astronomy. By the early 1800s, measuring stellar parallax had become astronomy's great challenge. It was the Holy Grail. Everyone knew it should be possible in principle, but nobody could actually do it. The failure wasn't from lack of trying. Dozens of skilled astronomers across Europe spent years on the problem. Some claimed success publishing measurements that other astronomers couldn't replicate. The claimed distances varied wildly, suggesting the measurements weren't reliable. The distances were too great, and the measurements too difficult for the instruments of the time. But one man was about to change everything. Friedrich Wilhelm Bessel was different from his predecessors. He was German, born in 1784 in the town of Minden in Westphalia. Interestingly, Bessel didn't start out as an astronomer. He began his career as an accountant for a trading company, but he taught himself mathematics and astronomy in his spare time. He was particularly interested in navigation and studied how to calculate positions using astronomical observations. At age 20, Bessel calculated the orbit of Halley's Comet using old observations. He did this purely as a hobby, but his work was so good that a professional astronomer Heinrich Olbers noticed it and helped Bessel get a position as an assistant at a small observatory. By age 26, Bessel was appointed director of a new observatory being built in Königsberg. He would spend the rest of his career there, making it one of Europe's leading observatories through the quality of his work. Bessel became one of the most meticulous scientists of his generation. He was obsessed with precision and error analysis. This was still a time when many scientists took measurements somewhat casually, writing down whatever their instruments showed, without carefully considering all the sources of error. Bessel was different. He didn't just take measurements. He analyzed every possible source of error, built mathematical models to account for them, and repeated observations until he was absolutely certain of his results. He studied how atmospheric refraction changed with temperature and humidity. Air acts like a lens bending light that passes through it. The amount of bending depends on air density, which varies with temperature, pressure, and water vapor content. Bessel made extensive measurements of these effects and developed correction formulas. He measured how his telescope's metal parts expanded and contracted with even small temperature changes. A brass tube might expand by a millimeter or more with a 10-degree temperature change. That sounds small, but it's enough to throw off the precise angular measurements needed for parallax. Bessel attached thermometers to his telescope and measured its length at different temperatures, developing correction factors. He tracked the mechanical play in his mount, the wobbles in his building's foundation, even the effect of wind pressure on the observatory dome. Every possible source of error was studied, measured, and accounted for. This level of care was unusual for the time and is exactly what was needed to detect parallax. But Bessel wasn't just a careful observer. He was a world-class mathematician. He developed what are now called Bessel functions, mathematical tools that are still used today in physics and engineering. These functions have applications in wave propagation, heat conduction, and electromagnetic fields. They arose from his astronomical work, showing how deeply he understood the mathematics underlying his observations. Bessel also learned from the failures of those who came before him. He studied Hooke's mistake with aberration and made sure he understood stellar aberration thoroughly. He examined Herschel's work with double stars and learned about binary systems. Every failed attempt by previous astronomers became a lesson about error sources to avoid. He was standing on the shoulders of giants, but he was also learning from their mistakes. At Königsberg Observatory, Bessel built a culture of precision. He trained his team to the same exacting standards. Every assistant had to learn error analysis. Double-checking and triple-checking every measurement became routine. Detailed logs were kept of every observation. Each entry recorded the exact time, air temperature, barometric pressure, wind conditions, cloud cover, and instrument settings. Nothing was left to chance or memory. This culture of precision became Königsberg's trademark. Bessel had the psychology of an obsessive scientist. He knew parallax was possible in principle, but he also knew it was at the edge of what was physically achievable with the technology available. He wasn't hasty, like Hooke, rushing to publish a result that turned out to be wrong, but he also wasn't overly cautious, like Henderson would be sitting on data for years out of fear. Bessel found the perfect balance between confidence and caution. His attitude was, I will measure it, or I will know why it cannot be measured. By the 1830s, Bessel was ready. He had the best telescope in Germany. He had the mathematical tools to model every error source. He had a deep understanding of atmospheric effects, temperature corrections, and mechanical limitations. He had a team trained to his exacting standards. He had patience. He just needed the right target. In 1837, Bessel decided to tackle the parallax problem directly. But he didn't just point his telescope at any random star. He chose his target carefully and strategically, and that choice would make history. Bessel chose his target with the precision of a strategist selecting battlefield terrain. He picked a star called 61 Cygni, located in the constellation Cygnus the Swan. It wasn't particularly bright. In fact, you need a small telescope to see it clearly. Under dark skies with good vision, you might barely glimpse it, but most people would miss it entirely. It's what astronomers call a fifth magnitude star, at the limit of naked eye visibility. So why this obscure dim star? Because 61 Cygni had one crucial property that suggested it might be relatively close to Earth. It moved across the sky faster than almost any other star. This motion isn't parallax. It's called proper motion, the star's actual movement through space over time. Most stars have such small proper motions that they appear fixed even over human lifetimes. The constellations look the same now as they did to ancient astronomers 2,000 years ago. But a few nearby stars have measurable proper motion, and Bessel reasoned that a star with high proper motion was probably relatively nearby. Think about watching cars on a highway from an overpass. The cars on the near lanes seem to zoom past, while distant cars barely seem to move. Same principle applies in space. Nearby stars, moving at typical stellar velocities, show larger proper motions than distant stars moving at the same speed. 61 Cygni has one of the largest proper motions known at the time, suggesting it was a nearby star and therefore a good parallax target. Bessel's logic was sound and strategic. From August 1837 through August 1838, Bessel made hundreds of observations using a specialized instrument called a heliometer. A heliometer is essentially a telescope with a split objective lens. The front lens of the telescope is cut in half, and one half can be slid sideways relative to the other. This creates two images of whatever you're looking at. By adjusting how much you slide the lens, you can superimpose the two images or separate them by precise amounts. This design lets you measure tiny angles with remarkable precision. If you're measuring the separation between two stars, you can put one star image from the left lens onto the other star image from the right lens and read off the separation from how far you had to slide the lens. Bessel's heliometer could measure angles down to about 1/10 of an arcsecond under good conditions. This was cutting-edge precision for 1837. But Bessel didn't just point his telescope at 61 Cygni and measure its position. That wouldn't work because he'd have no reference frame. The telescope itself might shift position slightly, or the whole building might settle. You need reference points. Instead, Bessel observed multiple reference stars in the same field of view. These were stars chosen to be so distant that their parallax would be essentially unmeasurable, effectively at infinite distance. Every clear night, weather permitting, Bessel measured the angular separation between 61 Cygni and these reference stars. He would measure the distance from 61 Cygni to reference star A, then to reference star B, then to reference star C. Multiple measurements, multiple references, all to maximize accuracy and catch any systematic errors. Over the course of months, as Earth moved around its orbit, 61 Cygni traced out a tiny ellipse against the background of reference stars. In January, Earth was on one side of its orbit, and 61 Cygni appeared slightly shifted in one direction. In April, Earth had moved a quarter of the way around its orbit, and 61 Cygni appeared shifted differently. In July, Earth was on the opposite side of the orbit, and the shift reversed. By October, the cycle continued. The size of that ellipse directly gave the parallax, but extracting that signal required dealing with a host of complicating factors, each much larger than the effect Bessel was trying to measure. Atmospheric refraction bends starlight, and the amount of bending changes with the star's altitude above the horizon, the air temperature, the humidity, even the barometric pressure. A star near the horizon might appear displaced by half an arc minute or more. That's 30 arc seconds, about 100 times larger than the parallax Bessel was measuring. He had to measure or calculate all these effects and subtract them out. The telescope's metal parts expanded when warm and contracted when cold. Even a change of a few degrees could shift the telescope's alignment by amounts larger than the parallax signal. The mount had tiny amounts of mechanical play that changed depending on which direction the telescope pointed. Point the telescope east, and gravity pulls on the tube one way. Point it west, and gravity pulls differently, causing small flexures. Earth's axis precesses like a wobbling top, causing all stellar positions to drift slowly over time. This is a tiny effect over 1 year, but Bessel had to account for it. Then there's aberration, the effect Hooke had mistakenly identified as parallax a century and a half earlier. Aberration makes stars appear shifted in the direction of Earth's motion by about 20 arc seconds, much larger than parallax. Bessel had to calculate and remove the aberration effect from every measurement. He observed at different times of night to see how changing altitude affected measurements. Higher in the sky means less atmosphere, to look through less refraction to account for. He recorded air temperature for every observation. He measured barometric pressure. He even noted wind conditions, because wind can shake the telescope and building. He measured the expansion and contraction of his telescope with thermometers attached to the metal tube. He developed mathematical formulas relating temperature to telescope length. He built models of mechanical flexure. Every error source got its own mathematical treatment. Only after accounting for everything else, after months of painstaking analysis, could he isolate the tiny parallax signal buried in the noise. A typical observing night in winter 1837 went like this. At 6 in the evening, Bessel would check the weather. Skies clear, seeing conditions good. At 7, he'd begin warming up the instruments. The heliometer needed stable temperature. He'd check the thermometers attached to the telescope and record baseline readings. By 8, when 61 Cygni had risen high enough above the horizon to minimize atmospheric interference, the first observations would begin. From 8 to 11, he'd run through his sequence of measurements. Measure 61, Cygni to reference star. 3 times. Measure 61, Cygni to reference star, B 3 times. Measure 61, Cygni to reference star, C 3 times. Each measurement took 10 to 15 minutes, total observing time about 90 minutes. At 11, he'd record all the data: temperature readings, barometric pressure, wind conditions, seeing quality rated on a scale of 1 to 5. By midnight, he'd return to his warm office to begin preliminary calculations, checking for obvious errors. By 2 or 3 in the morning, he'd finally retire. For 13 months, the mental and physical toll was enormous. Northern Germany winters are harsh. Short days, long nights, frequent clouds, rain, snow. Bessel had to observe every clear night because he couldn't afford to miss opportunities. His sleep schedule became completely irregular. The physical exhaustion was relentless. Standing in a cold observatory for hours, eyes strained from looking through the eyepiece, hands numb from cold while trying to write precise measurements, back aching from awkward positions required to use the heliometer. But worse than the physical exhaustion was the doubt. Midway through the campaign in the spring 1838, Bessel began to see hints of the signal, but the noise was still large. A question haunted him. Is this real parallax or another systematic error I haven't found? Am I about to make the same mistake as Hooke? Unlike Hooke, Bessel didn't rush to publish. Unlike Henderson, Wood Bessel didn't sit on his data too long. He continued observing, continued analyzing, built confidence slowly, methodically. Bessel didn't work alone. He had a team of assistants recording data, maintaining instruments, doing preliminary calculations, checking for errors. But the final analysis was his alone. I must be certain before I announce, he told his team. The weight of 2,000 years of failure sat on his shoulders. The weather statistics tell their own story. From August 1837 to August 1838, there were 365 days. Of those, only about 120 nights were clear enough to observe just 33%. And of those, Bessel actually conducted observing sessions on only about 80 nights. Usable data came from perhaps 60 nights. That means 305 days of waiting, checking the weather every evening, disappointment when clouds rolled in, frustration when skies were nearly clear, but not quite good enough. Northern Germany wasn't an ideal location for astronomy, but Bessel made it work with what he had. After each observation came the data processing hell. Raw numbers had to be processed before the next observation. Apply atmospheric refraction correction. Apply temperature correction. Apply aberration correction. Apply precession correction. Check for mechanical flexure. Calculate relative position. Each calculation took 30 to 60 minutes by hand. Each was an opportunity for arithmetic error. Everything had to be double-checked. The process couldn't be automated. This was before computers, before calculators. Only brain paper and logarithm tables. Then in late August 1838 came the breakthrough moment. Bessel completed his final analysis. He plotted all the data points, and there it was. The ellipse was clear. Not perfect. There was scatter in the measurements, but the pattern was unmistakable. After months of doubt, certainty arrived, like dawn breaking. This is real. This is parallax. His measurement, 0.314 arcseconds. To appreciate how small this is, imagine a dime held at arm's length about 60 centimeters away. The width of that dime, as seen from your eye, is an angle about 20,000 times larger than what Bessel measured. Or think of it as the width of a human hair seen from 100 meters away, or the angle subtended by the period at the end of this sentence seen from across a football field. After 2,000 years, we finally knew. From this measurement, using basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light years away. That's roughly 97 trillion kilometers. To put this in perspective, if you could somehow drive to 61 Cygni at highway speed, say 100 kilometers per hour, the trip would take about 110 million years. Modern measurements with better instruments give 11.4 light years, so Bessel was remarkably close accurate to within about 10%. Extraordinary for 1838. This was extraordinary work. 13 months of nearly continuous observations. Bessel had to observe on every clear night, which in northern Germany means dealing with clouds, rain, and short winter days. He made hundreds of individual measurements. Then came months of mathematical analysis, careful consideration of every possible error source, calculations done entirely by hand using logarithm tables, because electronic calculators wouldn't exist for another century. It's precisely why nobody had succeeded before. The level of precision required was far beyond what seemed possible with 1838 technology. The measurement was at the very edge of what was physically achievable with the best instruments and techniques available. But Bessel managed it through pure, obsessive attention to detail, mathematical skill, and relentless patience. Within months of Bessel's announcement in late 1838, the floodgates opened. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published parallax measurements for Alpha Centauri. Interestingly, Henderson had actually made his observations before Bessel, starting back in 1832. He had measured Alpha Centauri's position carefully over many months. But Henderson was cautious, perhaps too cautious. He saw a shift in position that looked like parallax, but he wasn't completely confident in his results. He worried about systematic errors. He questioned whether his instruments were accurate enough. So he sat on his data, continuing to analyze it, hesitating to publish. When Bessel's announcement came through in early 1839, Henderson realized his own measurements were valid and rushed to publish. His data was actually better than Bessel's in some ways because Alpha Centauri is brighter and closer, making the parallax larger and easier to measure. Alpha Centauri turned out to be even closer than 61 Cygni, at about 4.4 light years. This is interesting from a history of science perspective. Henderson actually made the first stellar parallax measurements, but Bessel gets credit for the discovery because Bessel published first. This happens sometimes in science. The person who publishes first gets the credit, even if someone else did the work earlier. It's why scientists often rush to publish as soon as they have solid results. Friedrich Georg Wilhelm von Struve, working at the Dorpat Observatory in what's now Tartu, Estonia, measured Vega's parallax shortly after Bessel's and Henderson's announcements. Struve was another meticulous observer who had been working on the parallax problem for years. Vega is much farther than the other two stars at about 25 light years, making its parallax even tinier and harder to measure. Struve's measurement was less accurate than Bessel's or Henderson's, but it was still a genuine detection and an incredible achievement. Suddenly, after 2,000 years of complete mystery, about stellar distances, we had distances to 3 stars, and more were coming. Astronomers worldwide began parallax programs. Within a few years, distances to dozens of stars had been measured. By the early 1900s, hundreds. By the mid-20th century, thousands. Each measurement confirmed that stars were scattered at enormous distances, far beyond anything in the solar system. The nearest star, Alpha Centauri, was 40 trillion kilometers away. That's about 270,000 times farther than the Sun. Sirius, one of the brightest stars in our sky, and fairly close by stellar standards, was 81 trillion kilometers away. More distant stars were even farther. In December 1838, Bessel presented his findings to the scientific community in Astronomische Nachrichten, the leading astronomy journal. The paper's title was Bestimmung der Entfernung des 61. Sterns des Schwans, meaning determination of the distance of 61 Cygni. The paper was thorough. Every observation was listed. Every correction was explained. Mathematical derivations were shown in detail. Error analysis was comprehensive. The scientific community's reaction was stunned silence, followed by explosive celebration. The German scientific community erupted in pride. A German astronomer had solved a 2,000-year-old problem. König Friedrich Wilhelm III of Prussia awarded Bessel with honors and increased funding for Königsberg Observatory. Students flocked to study under Bessel. Königsberg became a pilgrimage site for astronomers across Europe. The ripple effects spread quickly. The Paris Observatory immediately attempted to verify Bessel's results. The Royal Observatory at Greenwich began their own parallax program. Russian observatories scrambled to join the race. Italian astronomers were frustrated. They hadn't succeeded first. Competition heated up. Who could measure the most parallaxes? Who could reach the faintest, most distant stars? From 1839 to 1850, there was what you might call a parallax rush. Like a gold rush, but for stellar distances. Every major observatory was building better instruments, training observers in Bessel's methods, publishing claims, and fighting over priority. Some measurements were good, some were bad, some were outright wrong, but the progress was unmistakable. The public imagination was ignited. Before Bessel, most people thought stars were maybe a few hundred times farther away than the planets. After Bessel, there was a realization of the true cosmic scale. Popular books began appearing like The Plurality of Worlds in 1853, explaining these vast distances and speculating about life on other worlds. Newspapers ran articles. Public lectures were packed. People wanted to know, how far are the stars? This discovery fundamentally changed humanity's understanding of the universe's scale. Before parallax measurements, some astronomers thought the Milky Way might be only a few thousand astronomical units across perhaps 100 times the size of the solar system. After Bessel's work, it became clear the galaxy was millions of times larger. The Sun wasn't at the center of a small stellar system. It was one ordinary star among countless others scattered across distances so vast they were hard to comprehend. Our sense of cosmic scale expanded enormously. The universe went from being a solar system plus a sphere of stars just beyond the planets to being a vast space containing objects at distances requiring trillions of kilometers to describe. This was as revolutionary as Copernicus's discovery that Earth orbited the Sun, or Galileo's discovery that Jupiter had moons. but it was more visceral because now we could measure it, not just theory, actual numbers. The three pioneers had different fates. Bessel continued his work at Königsberg, making more stellar distance measurements. He even discovered that Sirius had an invisible companion, the first evidence of a white dwarf star. He died in 1846 at age 62, buried with honors, his legacy secure as the father of stellar astronomy. Henderson returned to Scotland and became Astronomer Royal for Scotland, but he never fully got the credit he deserved. There was some bitterness about being scooped. He died young in 1844, at age 46, largely forgotten by history, until recent years when his contribution was finally recognized. Struve lived longest of the three. He founded Pulkovo Observatory near St. Petersburg and became the greatest Russian astronomer of his era. He measured hundreds more parallaxes and created a dynasty. His son and grandson also became famous astronomers. He died in 1864 at age 71, celebrated and honored. As measurements accumulated, astronomers faced a practical problem. How do you communicate these enormous distances? Writing out 97 trillion kilometers gets tedious very quickly. Scientific papers were filled with huge numbers. Saying 657,000 astronomical units is awkward. Using multiples of the sun's distance helped somewhat, but it still wasn't ideal. They needed a better solution. Someone and history isn't entirely clear who first suggested it proposed defining a new unit based directly on parallax geometry. The idea was beautifully simple and came naturally from the measurement technique itself, and it would change astronomy forever. The idea was beautifully simple. Take a right triangle. One side of the triangle, the base is 1 astronomical unit. The distance from Earth to the Sun, the angle opposite that base at the vertex where the star sits, is 1 arcsecond. Now solve for the length of the long side of the triangle, the hypotenuse, which is the distance to the star. Using basic trigonometry, specifically, the tangent function this distance works out to approximately 206,265 astronomical units. In more familiar terms, that's about 30.9 trillion kilometers, or about 19.2 trillion miles. They called this distance the parsec, a contraction of parallax and arcsecond. The name itself tells you exactly how it's defined. Here's the crucial thing to understand. 1 arcsecond was chosen because it's a round number in the angular measurement system humans invented thousands of years ago. The Babylonians around 2000 BCE developed a base 60 number system. They divided circles into 360 degrees because 360 has many factors. It's divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, and more. This makes it easy to divide circles into halves, thirds, quarters, and so on. They divided degrees into 60 arc minutes because 60 is also highly divisible, and they divided arc minutes into 60 arc seconds for the same reason. This sexagesimal system, based on the number 60, is why we still measure time in 60-second minutes and 60-minute hours. The Babylonians invented it, the Greeks adopted it, and it spread throughout the ancient world and persisted to today. But there's nothing physically special about this choice. It's pure mathematical convenience based on ancient numbering preferences. An alien civilization using a different angular system might divide circles into some other number of degrees and define their angular units differently. The parsec is a consequence of human choices about how to measure angles, not anything fundamental about the universe. And virtually no star sits exactly 1 parsec from Earth. Our nearest stellar neighbor, Proxima Centauri, is about 1.302 parsecs away, according to the latest Gaia satellite measurements. That's the most accurate distance we have measured to 4 significant figures. The bright star Sirius, prominent in winter skies, is about 2.64 parsecs. Vega, one of the brightest stars in summer skies, is about 7.68 parsecs. Bessel's 61 Cygni is about 3.5 parsecs. The parsec doesn't mark any natural cosmic boundary. It's not the distance at which any particular physical process occurs. Stars don't start behaving differently at 1 parsec. There's no sphere of special significance at that distance. It's simply the distance that makes parallax arithmetic convenient, defined by an arbitrary angular choice. But that convenience turned out to be enormous for working astronomers. For astronomers doing parallax measurements every single day, the parsec had one massive advantage over any other distance unit. Measure a star's parallax in arcseconds, and its distance in parsecs is just 1 divided by that number. The relationship is direct and transparent. If a star shows a parallax of 0.5 arcseconds, it's 2 parsecs away. 0.25 arcseconds, 4 parsecs. 0.1 arcseconds, 10 parsecs. 0.05 arcseconds, 20 parsecs. Mental arithmetic, no calculator needed. No complex conversions. No looking up tables. Just invert the parallax and you have the distance. When you're processing hundreds or thousands of measurements by hand, which is what astronomers did before computers, this directness is invaluable. Imagine you're working through a notebook full of parallax measurements. Star A 0.15 arcseconds, that's 6.67 parsecs. Star B 0.28 arcseconds, that's 3.57 parsecs. Star C 0.08 arcseconds, that's 12.5 parsecs. You can do this math in your head while working through the observations. The relationship is transparent. If you measure a parallax of 0.05 arcseconds, you instantly know the distance is 20 parsecs. If you make a mistake somewhere and accidentally get 0.5 arcseconds instead, the distance comes out to 2 parsecs, and you immediately know something went wrong, because that would make the star one of the very nearest in the sky, which should have been obvious from its brightness and other properties. Compare this to using other units. Using kilometers or miles would require multiplying by large conversion factors every single time. The number of kilometers in 1 parsec is 30.9 trillion. Every parallax measurement would require multiplying or dividing by this enormous number. Using astronomical units would require dividing by 206,265 every time. Using light years would require multiplying by about 3.26 every time. Each calculation is an opportunity for arithmetic errors. The parsec eliminates that. The conversion is built into the definition. The unit was designed specifically to make the most common calculation in stellar astronomy as simple as possible. Think about what this means in practice. An astronomer in 1850 sitting at a desk with only paper pen and logarithm tables measuring parallaxes of dozens of stars, can instantly convert measurements to distances. No arithmetic, no looking anything up, just immediate understanding. If parsecs seem arbitrary and unintuitive, to outsiders that's because they are arbitrary. But to professional astronomers doing parallax work, they're the most natural thing in the world. The unit emerged organically from the measurement technique and made the astronomers' lives easier. By the late 1800s, astronomers had measured parallaxes for dozens of stars. Each measurement confirmed that stars were scattered at enormous distances far beyond anything in the solar system. The parallax technique was working. Distances were being measured reliably. The parsec became the natural unit for expressing those distances. It wasn't an official decision by any committee or scientific organization. It happened organically because it was genuinely useful. Astronomers started using it in papers because it simplified their work. Other astronomers reading those papers adopted it because it made the results easier to understand. Catalogs started listing distances in parsecs. Textbooks explained the concept. By 1900, it had become the default unit for stellar distances in professional astronomy, not because anyone mandated it, but because it worked. As telescope technology improved and observations reached deeper into space, astronomers needed larger multiples of the parsec. By the early 1900s, they were measuring distances to star clusters, hundreds or thousands of parsecs away. Writing out 3,000 parsecs repeatedly was tedious. So they borrowed the metric system's prefixes and invented the kiloparsec, meaning 1,000 parsecs. A typical globular cluster, a spherical collection of hundreds of thousands of old stars, might be 15 kiloparsecs away. The center of our Milky Way galaxy is about 8.2 kiloparsecs from Earth. Understanding why the parsec became absolutely foundational to modern astronomy requires understanding what happened in the early 20th century. This is when astronomy transformed from a science of individual observations by single astronomers to a science of massive, systematic surveys producing huge data sets. The Harvard College Observatory, under the direction of Edward Pickering, starting in 1877, undertook an ambitious project. They decided to photograph the entire sky, visible from both their Massachusetts location and from an observatory they set up in Arequipa, Peru, to cover the southern sky. Over several decades, working with relatively primitive photographic plates, they created over 500,000 photographs, each capturing thousands of stars. This was an unprecedented amount of data, more information than any previous astronomical project had generated. Pickering needed people to analyze it all, examine each plate, measure star positions and brightnesses, classify stellar spectra. This was tedious, time-consuming work requiring good eyesight attention to detail and some mathematical skill. Pickering hired a team of women to do this work. He called them computers because their job was to compute stellar properties from the photographic plates. These women, despite being paid far less than male astronomers, and often receiving no formal credit for their work, made some of astronomy's most important discoveries. Annie Jump Cannon classified over 350,000 stellar spectra, developing the classification system still used today. Williamina Fleming discovered over 300 variable stars and 10 novae. Cecilia Payne-Gaposchkin showed that stars are made primarily of hydrogen and helium, not the heavier elements found in Earth. But for our story, the most important of the Harvard computers was Henrietta Swan Leavitt. She was analyzing variable stars in the Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere. Variable stars are stars whose brightness changes over time. Some vary randomly, flaring up and dimming unpredictably, but others pulsate with regular periods, getting brighter and dimmer in a repeating cycle. Leavitt was studying a particular type called Cepheid variables, named after the star Delta Cepheid, which pulsates with a period of about 5 days. In 1912, after years of patient work, measuring Cepheid periods and brightnesses, Leavitt made a revolutionary discovery. She found that Cepheid variables' pulsation periods directly relate to their intrinsic luminosity. Longer period Cepheids are genuinely brighter stars. A Cepheid that pulsates with a 30-day period is intrinsically brighter than one with a 10-day period, which is brighter than one with a 3-day period. The relationship is tight, predictable, and quantifiable. This changed everything for distance measurements. If you observe a Cepheid variable anywhere in the universe, measure its pulsation period, you immediately know its true intrinsic brightness. Compare that to how bright it appears from Earth, and you can calculate how far away it is using the inverse square law. Light spreads out as it travels, so brightness falls off as the square of distance. If something appears 4 times dimmer than expected, it must be twice as far away. Cepheids became astronomy's standard candles objects, whose true brightness is known letting you measure distance by comparing true to apparent brightness. The crucial detail is that Cepheids are genuinely luminous stars. A typical Cepheid shines with the light of thousands of suns. They're bright enough to be seen in other galaxies, even millions of parsecs away. This let astronomers measure distances far beyond the reach of parallax. Parallax only works for nearby stars. With early 20th century technology, parallax was reliable out to maybe a few hundred parsecs for the brightest stars. For most stars, much less. Cepheids extended distance measurements to millions of parsecs, thousands of times farther than parallax could reach. But here's the key point for understanding the parsec's dominance. To calibrate the Cepheid period luminosity relationship, you need to know the actual distances to some Cepheids. You need to establish exactly how much brighter a 30-day Cepheid is than a 10-day Cepheid. The only way to measure those distances was parallax for the nearest Cepheids, or statistical parallax methods that average over many stars. The entire cosmic distance ladder, all the techniques that let us measure distances to far galaxies and determine the universe's scale, all of it traces back to those original parallax measurements. Parallax gives distances to nearby stars in parsecs. Those parsecs calibrate the Cepheid relationship. Cepheids give distances to galaxies in megaparsecs. Galaxies calibrate type Ia supernovae. Supernovae extend to gigaparsecs. Every step builds on the previous one, and every measurement comes out in parsecs, because that's what parallax naturally produces. So the parsec didn't just become standard for nearby stars, it became the foundation for all astronomical distance measurements. Every subsequent technique was calibrated using Parsec distances. In 2013, the European Space Agency launched a satellite called Gaia with an extraordinarily ambitious goal measure, precise positions and distances for over 1 billion stars. That's roughly 1% of all the stars in our Milky Way galaxy. Gaia carries 2 telescopes that continuously scan the sky. As the satellite slowly rotates, each star passes through the field of view multiple times over the mission lifetime. The satellite measures each star's position with incredible precision, down to micro arc seconds for the brightest stars. That's 1/1,000,000th of an arc second. This level of precision lets Gaia detect parallax for stars much farther away than was ever possible before. By 2022, Gaia had released data on over 1.8 billion stars. And every single distance in the Gaia catalog is reported in parsecs. The parsec had become more entrenched than ever. While professional astronomers embrace the parsec universally, across all subdisciplines, popular science went a completely different direction. The space race of the 1950s and 1960s ignited massive public interest in astronomy and space exploration. The Soviet Union launched Sputnik in 1957, the first artificial satellite. Yuri Gagarin became the first human in space in 1961. NASA's Apollo program culminated in the moon landing in 1969. Suddenly, millions of people wanted to learn about the cosmos. Popular books flooded the market. Magazine articles explained black holes and quasars. Television shows explored the planets. Museums built planetariums. All of this needed to communicate astronomical distances to general audiences, and they all used light years instead of parsecs. Carl Sagan's Cosmos television series, which aired in 1980 and was seen by over 600 million people worldwide across 60 countries, used light years exclusively. When Sagan talked about Alpha Centauri, he said it was 4.24 light years away. When he discussed the Milky Way's size, he said it was 100,000 light years in diameter. When he mentioned distant galaxies, he gave their distances in millions or billions of light years. Not once, in 13 episodes, did he use the word parsec. This made perfect sense for public communication. The light year concept explains itself. Light is the fastest thing in the universe. Everyone knows that. A year is a time span everyone understands intuitively. So a light year is obviously a huge distance, the distance light travels in 1 year at its incredible speed. The name itself conveys the concept. It's intuitive and evocative. The parsec, in contrast, requires extensive explanation. You have to explain what parallax is and why we use it. You have to explain what an arcsecond is and where that angular unit comes from. You have to explain why astronomers chose that particular angle for their definition. You have to draw diagrams showing the geometry. Even after all that explanation, most people find it abstract and unintuitive. It doesn't connect to everyday experience the way a light year does. The light year also has poetic resonance. When you say Andromeda is 2.5 million light years away, people immediately understand that we're seeing light that left Andromeda 2.5 million years ago. We're looking back in time. The photons striking our telescopes began their journey when our distant ancestors were just learning to make stone tools. That's evocative and meaningful. Saying Andromeda is 780 kiloparsecs away doesn't have the same impact. It's accurate and professional astronomers use it, but it doesn't resonate emotionally. it doesn't immediately connect to anything in human experience. So, a split emerged that persists to this day. Professional astronomers use parsecs in their research. Every research paper, every professional catalog, every technical discussion uses parsecs or kiloparsecs or megaparsecs, but popular science uses light years. Every news article, every documentary, every museum exhibit uses light years. Same astronomer, same galaxy, different number, depending on the audience. An astronomer writing a paper for the Astrophysical Journal will say a galaxy is 300 megaparsecs away. That same astronomer, interviewed for a New York Times article about the same galaxy, will say it's about 980 million light years away. They're the same distance, just expressed in different units for different audiences. This dual system creates some confusion. People reading popular astronomy books think in light years. Then, if they take an astronomy course or try to read research papers, suddenly everything is in parsecs. They have to learn the conversion factor 3.26 light years per parsec and mentally convert while reading. It's a barrier to engagement with professional astronomy. But both communities have legitimate reasons for their choices. Astronomers keep using parsecs because it connects directly to their measurement techniques and because their entire infrastructure assumes parsec units. All their databases store distances in parsecs. All their software expects parsec inputs. All their formulas are written with parsecs. Popular science keeps using light years because audiences find them more understandable and because the name itself is evocative and memorable. Science communicators want to engage people's imaginations. Saying a star is 4 light years away makes people think about light traveling for 4 years. That's interesting and thought-provoking. Saying the same star is 1.3 parsecs away just sounds technical and dry. The parsec became the tribal knowledge of the astronomical community, a marker of insider status. If you know what a parsec is and can work with it fluently, you're part of the club. If you don't, you're an outsider. This isn't deliberate gatekeeping. It's just how specialized communities develop their own language and conventions. But it does create a boundary between professional astronomy and everyone else. The parsec's dominance in professional astronomy has been reinforced and extended enormously by the sheer weight of accumulated infrastructure. By the early 21st century, the astronomical community had built an enormous superstructure around the parsec that would be extraordinarily difficult to dismantle. Consider the databases. Every major astronomical database, from the Simbad Astronomical Database in Strasbourg to the NASA Extragalactic Database to hundreds of specialized catalogs, stores distances primarily in parsecs. These databases contain measurements from millions of objects accumulated over decades. Converting all of this data to a different unit would require changing not just the numbers, but all the associated metadata, all the query interfaces, all the documentation. Every paper that cited the old database, entries would suddenly reference numbers that don't match the current database. The confusion would be enormous. Then there's the software. Astronomers use thousands of specialized software packages for data analysis, telescope control, observation planning, and theoretical modeling. These programs expect parsec inputs. They're written with parsec-based formulas. Converting them all would require rewriting millions of lines of code. And it's not just a matter of multiplying by a conversion factors. Many astronomical calculations involve complex equations where the choice of units affects multiple terms. Change the distance unit, and you have to carefully trace through every equation to make sure the conversions are correct everywhere. The textbooks present another challenge. Every astronomy textbook, from introductory undergraduate level through advanced graduate courses, teaches parsecs. Generations of students have learned to think in parsecs. Changing to a different unit would require rewriting every textbook, updating every problem, set revising every exam. Professors would have to retrain themselves to think in the new unit. Their intuitions built over decades of working in parsecs would become liabilities. A professor who instantly knows that a galaxy at 300 megaparsecs is at a certain distance scale would have to rebuild that intuition from scratch in a new unit. This is what economists and sociologists call a collective action problem. Everyone might benefit if everyone switched to a more accessible or universal unit, like light years or meters. But nobody wants to be the first to switch, because doing so creates individual costs through friction with existing infrastructure and norms. The group would benefit from coordination, but individuals are punished for deviating unilaterally. If you submit a paper reporting distances in light years when everyone else uses parsecs, reviewers might flag it as non-standard. They might request you convert to parsecs before publication. Using non-standard units marks you as an outsider or someone who doesn't understand field conventions. Database managers might hesitate to ingest your data if it uses non-standard units. They'd need to verify the units are correctly flagged in metadata. They'd need to ensure conversion factors are applied correctly. It's easier to require standard units, and parsecs are what they require. The most famous unit, conversion error in space history, illustrates just how dangerous mixing unit systems can be. In 1999, NASA launched the Mars Climate Orbiter, a spacecraft designed to study the Martian atmosphere and climate. The mission cost $327 million. The spacecraft was lost because one piece of software, developed by Lockheed Martin, generated thrust data in pound force seconds an imperial unit. Another piece of software, developed by NASA, expected Newton seconds an SI unit. Nobody caught the discrepancy during testing. The spacecraft's trajectory calculations were wrong by a factor of about 4.4. Instead of entering orbit safely at an altitude of about 140 kilometers above Mars, it passed at only 57 kilometers, well within the Martian atmosphere. The spacecraft burned up. $327 million lost to a unit conversion error. That's an extreme example, but it illustrates the real dangers of working with multiple unit systems. Every interface between systems is a potential failure point. The more unit conversions required, the more opportunities for errors, and astronomy interfaces with many other fields. Gravitational wave astronomy brings together observational astronomers, theoretical physicists, experimental physicists, and computer scientists. Physicists modeling gravitational wave signals work in SI units because the equations of general relativity are naturally expressed in meters and seconds. but astronomers analyzing the host galaxies expect distances in megaparsecs. Every collaboration requires careful unit tracking and conversion. Mistakes are easy to make. Planetary science presents similar challenges. Distances within the solar system are often expressed in astronomical units, but sometimes in kilometers, depending on context. Mission design for space probes needs distances in kilometers because that's what navigation software expects. But orbital dynamics calculations sometimes use astronomical units for convenience. In astrobiology, when discussing potentially habitable exoplanets, do you report distances in parsecs or light years? Scientific papers use parsecs. Popular articles use light years. Press releases need to include both. The dual system creates friction and inefficiency. The Parsec's defenders argue that these interface problems exist regardless of which unit astronomy uses internally. Physics will always use meters. The public will always prefer intuitive units. The question is whether changing astronomy's internal standard would reduce or increase the total friction. And the answer isn't obvious. Switching to light years would make public communication easier, but wouldn't help with physics interfaces. Switching to meters would help with physics, but make public communication harder and disconnect from the parallax measurement technique. The parsec, for all its quirks, at least connects directly to how distances are measured. That connection has value beyond mere convenience. Individual astronomers have little incentive to deviate from standard practice. The costs are immediate and personal. Your papers might be rejected. Your data might not be included in catalogs. Your colleagues might view you as difficult or eccentric. The benefits are diffuse and uncertain. Maybe someday the field will thank you for pioneering a better system, or maybe you'll just have made your own work harder for no gain. So, astronomers stick with parsecs, not because parsecs are optimal by some objective measure, not because no alternative could possibly be better, but because the costs of switching are high and concentrated on those who switch, while the benefits are uncertain and would be spread across the entire field. The infrastructure grows and hardens over time. Each new catalog adds to the accumulation of parsec-based data. Each new survey builds on previous surveys' distance scales. Each new generation of students learns parsecs and internalizes them as natural. The barrier to change grows higher every year. Then in the 1920s, Edwin Hubble made one of astronomy's greatest discoveries. Those fuzzy spiral nebulae that astronomers had been cataloging for decades weren't gas clouds within our galaxy. They were separate galaxies' island universes, containing billions of stars, located at staggering distances. Hubble's discovery came from observing Cepheid variable stars in the Andromeda Nebula. Using the 100-inch telescope on Mount Wilson, at the time the largest telescope in the world, he could resolve individual stars in Andromeda. Some of these stars were Cepheid variables, which pulsate with regular periods. Using Henrietta Leavitt's period luminosity relationship, Hubble measured the periods of Cepheids in Andromeda, determined their true luminosities compared to how bright they appeared from Earth, and calculated the distance. The answer came out to about 280 kiloparsecs. Modern measurements give 780 kiloparsecs, so Hubble's initial distance was too small by a factor of nearly 3. but it was still clearly far beyond the Milky Way's boundaries. Writing that number repeatedly was tedious. So, astronomers invented the megaparsec, meaning 1 million parsecs. Andromeda is 0.78 megaparsecs away. Other galaxies turned out to be even farther. The Virgo cluster of galaxies is about 16 megaparsecs away. The Coma cluster is about 100 megaparsecs. The expansion of the universe was carrying distant galaxies away from us at speeds proportional to their distance. Hubble discovered this relationship in 1929, and it revolutionized our understanding of the cosmos. One of the most important numbers in all of cosmology is something called the Hubble constant. This quantifies the rate at which the universe is expanding. In the 1920s, Edwin Hubble, using Cepheid variables to measure galaxy distances and spectroscopy to measure their recession velocities, discovered a remarkable relationship. Distant galaxies are receding from us, moving away, as space itself expands, and the farther away they are, the faster they recede. The relationship is linear. Double the distance, double the recession velocity. The Hubble constant quantifies this relationship. Its value is somewhere around 67 to 74 kilometers per second per megaparsec, depending on which measurement method you trust. What this means is that for every megaparsec of distance, a galaxy's recession velocity increases by that many kilometers per second. A galaxy 1 megaparsec away recedes at about 70 kilometers per second. A galaxy 2 megaparsecs away recedes at about 140 kilometers per second. A galaxy 10 megaparsecs away recedes at about 700 kilometers per second. At large enough distances, recession velocities approach the speed of light. This isn't motion through space, but space itself expanding between us and the galaxy. Notice the units of the Hubble constant: kilometers per second per megaparsec, velocity per distance. The parsec is baked into the fundamental equation describing how fast the universe is expanding. You could convert to other units. Some cosmologists use inverse gigayears, which has dimensions of inverse time, making the expansion rate look like a frequency. But most use kilometers per second per megaparsec because that's how we measure it. We measure galaxy recession velocities in kilometers per second from spectroscopic redshifts. We measure distances in megaparsecs using the distance ladder. So, the natural units for the Hubble constant are kilometers per second per megaparsec. Using anything else requires conversions that don't add clarity. Recent measurements from different techniques disagree about the Hubble constant's exact value, and this disagreement is one of the biggest unsolved problems in cosmology. Observations of the cosmic microwave background, the afterglow of the Big Bang, analyzed using our best cosmological model with parameters from the Planck satellite, give a value around 67.4 kilometers per second per megaparsec. Measurements using the cosmic distance ladder, starting with parallax to calibrate Cepheids, and using Cepheids to calibrate type Ia supernovae, give a value around 73 kilometers per second per megaparsec. That's about an 8% disagreement. The two measurements have uncertainties of only about 2 or 3%, so they disagree at multiple sigma significance. This is genuinely worrying. Either one of the measurement techniques has a subtle systematic error nobody's found yet, or our standard cosmological model is missing something important. Maybe dark energy behaves differently than we think, changing its density over time. Maybe there's some unknown physics affecting cosmic expansion. Maybe neutrinos have slightly more mass than we thought. Maybe there's another particle we haven't discovered. This is called the Hubble tension, and resolving it is a major goal of observational cosmology. Teams around the world are working to either find the error in one of the measurement methods or figure out what new physics might explain the discrepancy. But notice that the entire debate is framed in parsecs. The Cosmic Microwave Background Team reports 67.4 kilometers per second per megaparsec. The Distance Ladder Team reports 73 kilometers per second per megaparsec. The units are assumed. Nobody suggests measuring the Hubble constant in different units, as observations pushed even deeper into the cosmos, revealing the large-scale structure of the universe itself. The gigaparsec emerged. That's 1 billion parsecs. Distant galaxy clusters sit at distances measured in hundreds or thousands of megaparsecs, or equivalently fractions of a gigaparsec, the edge of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang is about 14 gigaparsecs in comoving coordinates. We took a unit originally based on a convenient angular measurement for nearby stars and kept multiplying it by thousands because the universe kept getting bigger in our observations. At each stage, the parsec stuck around simply because converting everything to a new unit would have been more work than just adding a prefix. The infrastructure was already built around parsecs. All the formulas, all the catalogs, all the mental habits of astronomers assumed parsecs. Switching would have required coordinated effort across the entire field for unclear benefit. So, we went from parsecs to kiloparsecs to megaparsecs to gigaparsecs, each step extending the original unit to scales Bessel never could have imagined. The parsec that started as a convenient way to express distances to nearby stars became the standard unit for measuring the size of the observable universe itself. Several major observatories planned for the 2030s will shape astronomy for the next several decades, and all of them will further entrench the parsec through their data products and analysis software. The extremely large telescope being built by the European Southern Observatory in Chile's Atacama Desert will have a primary mirror 39 meters in diameter. That's over 128 feet. It will be the largest optical telescope in the world when completed. Construction costs exceed 1 billion euros. First light is expected around 2027. The ELT will study exoplanet atmospheres in unprecedented detail, potentially detecting biosignatures, chemical signs of life in the atmospheres of planets orbiting other stars. It will observe the most distant galaxies in the universe, seeing them as they were when the universe was young, less than 1 billion years after the Big Bang. It will study dark matter and dark energy, the mysterious components that make up 95% of the universe's mass energy content. It will track stars orbiting Sagittarius A star, the supermassive black hole at our galaxy's center. All of this science will produce distances in parsecs, because that's what astronomers designing the instruments and planning the observations expect. The data processing pipelines being written now assume Parsec units. The observation planning software expects target coordinates and distances in Parsec-based systems. The archive databases being designed will store everything in parsecs. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, is NASA's next major space observatory after James Webb. Named after NASA's first chief astronomer, it's designed for wide field surveys and will revolutionize studies of dark energy exoplanets through gravitational microlensing and galactic structure. Launch is currently planned for May 2027. Total mission cost will exceed $3.9 billion. Roman will survey huge areas of sky cataloging billions of stars and galaxies. It will measure distances to nearby galaxies through Cepheid variables and type Ia supernovae, refining measurements of the Hubble constant and trying to resolve the Hubble tension we discussed earlier. It will map the three-dimensional distribution of dark matter through weak gravitational lensing, where the gravity of dark matter slightly distorts the images of background galaxies. Every distance measurement will be in parsecs, because that's what the data processing pipelines output and what astronomical databases expect. The mission is being designed now in the 2020s with parsec-based infrastructure. That infrastructure will still be in use in 2050 and beyond, as astronomers continue analyzing Roman data decades after the mission ends. The Square Kilometer Array is an international radio telescope project that will eventually have a collecting area of 1 square kilometer spread across thousands of individual antennas in Australia and South Africa. It will be the most sensitive radio telescope ever built by several orders of magnitude. The first phase, SKA low in Australia, operating at low radio frequencies, and SKA mid in South Africa at higher frequencies, should be operational in the early 2030s. Construction costs will exceed 2 billion euros. SKA will study the cosmic dawn, the period when the first stars formed in the early universe, lighting up the cosmos for the first time. It will detect radio pulsars with exquisite timing, precision, using them to search for gravitational waves at frequencies that the space-based detectors can't access. It will map neutral hydrogen across the universe, tracing cosmic structure evolution over billions of years. Some scientists even hope it might search for radio technosignatures from advanced civilizations. All of these programs will involve distance measurements in parsecs. The science teams designing these instruments and planning observations are professional astronomers who think in parsecs. The correlator software that combines signals from thousands of antennas assumes parsec-based coordinates. The catalogs that will be produced will list everything in parsecs. These are multi-billion-dollar, multi-decade projects that will produce data for 50 years or more. The Hubble Space Telescope, launched in 1990, is still operating today, 35 years later. The data it has produced continues to be analyzed and reanalyzed. Scientists are still publishing papers using Hubble data, and all those papers use parsecs. The same will be true for ELT Roman and SKA. Their design decisions will influence astronomy well into the second half of the 21st century. Simply through continued use in flagship missions, the parsec will remain entrenched. Each new catalog adds to the accumulation of Parsec-based data. Each new survey builds on previous surveys' distance scales. The infrastructure grows and hardens. Switching becomes progressively more difficult as more depends on the existing system. But there is a counterbalancing trend. Software is becoming more sophisticated at handling unit conversions automatically. Modern astronomical databases don't just store numbers. They store numbers with metadata, indicating units, precision measurement, method, and provenance. Query a database for a galaxy's distance, specify what units you want in the output, and the system converts automatically. This capability already exists in many systems. The Simbad Astronomical Database, maintained by the Centre de Données Astronomiques de Strasbourg, stores distances primarily in parsecs, but can display them in light years on request. The NASA Exoplanet Archive provides distances in both parsecs and light years by default. These are proofs of concept showing that multi-unit support is technically straightforward. This functionality just needs to become more universal and user-friendly. Every major astronomical database and analysis tool should support seamless unit conversion. Users should be able to set preferences once and have everything display in their preferred units automatically. No manual conversion required. Machine learning algorithms are increasingly used to analyze astronomical data, discovering patterns humans might miss. Adding intelligent unit conversion to these systems is straightforward. The algorithms don't care whether inputs are in parsecs, light years, or meters. They work with numbers. Humans care about units because we need to interpret the numbers, but software can handle conversions invisibly. Systems could learn individual users' preferences through usage patterns. If an astronomer always queries distances and immediately converts to parsecs, the system learns to provide parsecs by default for that user. If a science communicator always converts to light years, provide light years. If a physicist working on gravitational waves wants meters, provide meters. Adaptive interfaces that learn user preferences already exist in other contexts. Email clients learn which messages you mark as spam. Music streaming services learn what songs you like. Applying this to astronomical unit conversion is natural and would reduce friction between different communities. This doesn't resolve the fundamental question of which unit is objectively better or more natural. Different communities will have different preferences based on their needs and training, but it makes the question less important in practice. The parsec can remain astronomy's native unit while becoming less of a barrier to outsiders because translation will be seamless and automatic. An interdisciplinary researcher working with astronomical data won't need to learn parsecs if their analysis software converts everything to their preferred units in the background. A science journalist won't need to manually convert distances when writing an article if the database query interface offers a convert to light years checkbox. A physics student won't stumble over parsecs in their first astronomy course if the textbook's online companion automatically shows all distances in whatever unit the student prefers. The technology to make units transparent already exists. It just needs to be deployed more widely and consistently. If that happens, the parsec's entrenchment becomes less problematic. It remains the field's internal standard, but interfaces with other communities become smoother. My prediction is that 50 years from now, professional astronomers will still primarily think and work in parsecs. The next generation of major observatories will ensure that. But the barriers parsecs create for outsiders will be lower because software infrastructure will handle conversions automatically. The parsec will remain astronomy's native language, but translation services will be built in and seamless. Let's bring this down to something more concrete and visceral. Understanding what a parsec means in terms of actual travel helps illustrate just how vast these distances are. Consider the Parker Solar Probe, NASA's mission to study the Sun's corona by flying closer to the Sun than any previous spacecraft. Launched in 2018, it uses multiple Venus flybys to gradually drop deeper into the Sun's gravity well, using gravity assists to reach incredible speeds. At its maximum speed during close approaches to the Sun, the Parker Solar Probe reaches about 192 kilometers per second. That's 119 miles per second. It's the fastest human-made object ever built, moving at about 0.06% of light speed. At this incredible speed, crossing just one astronomical unit from Earth to the Sun takes about 9 days. That's extraordinarily fast by human standards. But remember, one parsec is over 200,000 astronomical units. Proxima Centauri, our nearest stellar neighbor, sits at 1.302 parsecs away. If the Parker Solar Probe were heading toward Proxima Centauri, instead of orbiting the Sun, traveling in a straight line at its peak speed, the journey would take approximately 6,600 years. Think about that. 6,600 years ago, humans were just developing agriculture in the Fertile Crescent. Writing hadn't been invented yet. The pyramids of Egypt wouldn't be built for another 2,000 years. The entire span of recorded human history is only about 5,000 years. A journey to the nearest star at our fastest achievable speed would take longer than all of human civilization. And that's to the nearest star, the closest possible destination outside our solar system. Sirius, one of the brightest stars in our sky, and fairly close by stellar standards, is at 2.64 parsecs. That would take over 13,000 years. Vega, prominent in summer skies, is at 7.68 parsecs. That's over 33,000 years of travel. These aren't abstract numbers. They're the brutal reality of cosmic distances versus our current technology. Even our fastest spacecraft, pushing the boundaries of what chemical rockets and gravity assists can achieve, would require thousands of years to reach even the nearest stars. This is why interstellar travel remains science fiction for now. The distances are simply too vast for any propulsion system we can currently build. Chemically propelled rockets are limited by the energy density of chemical bonds. You can't extract more energy from burning hydrogen and oxygen than the chemistry allows. Nuclear rockets could do better, maybe reaching a few percent of light speed, reducing the trip to Proxima Centauri to perhaps a century instead of thousands of years. Theoretical concepts like nuclear pulse propulsion, which involves detonating nuclear weapons behind a spacecraft and riding the shockwave, might reach 10% of light speed. Laser-pushed light sails, using powerful lasers to accelerate tiny probes, might reach 20% of light speed. But all of these are theoretical. Nobody's actually built them, and even at 20% of light speed, Proxima Centauri is still over 20 years away. That's assuming you can accelerate to that speed, which would require enormous infrastructure, unless we develop fundamentally new physics, perhaps something like an Alcubierre warp drive that somehow gets around relativity's cosmic speed limit. Practical interstellar travel with human crews remains far beyond our capabilities. We can barely get to Mars, and that's only 0.00003 parsecs away. When we talk about interstellar distances in public discourse, light years dominate completely. News articles about exoplanets always give distances in light years. Science fiction uses light years. Popular books use light years because light years make travel time intuitive. If something is 4.2 light years away, like Proxima Centauri, you immediately understand that light takes 4.2 years to get there. At 1% of light speed, a spacecraft would take 420 years. At 10%, 42 years. At 50%, 8.4 years. The calculation is direct and obvious. Everyone can do it in their head. Parsecs don't offer this advantage. 1.3 parsecs away means what in terms of travel time? You have to first convert to light years, multiply by 3.26, then do your calculation. When we eventually detect biosignatures in an exoplanet's atmosphere confirming life beyond Earth, the distance to that planet will become one of the most discussed numbers in human history. Media coverage will be overwhelming. Every news outlet worldwide will report the discovery. Every person on Earth will hear about it, and they will almost certainly give the distance in light years, not parsecs, because that's what general audiences can understand. Imagine the headlines: life found on planet 40 light years away. That resonates with people. They understand that light from that planet takes 40 years to reach Earth. They grasp the timescales involved. They can imagine what 40 years means in human terms. Life found on planet 12, 0.3 parsecs away, sounds technical and alienating. It requires explanation that most news articles won't provide. It creates a barrier between the discovery and public understanding. If we ever reach the point of seriously planning interstellar missions, perhaps using breakthrough technologies like nuclear, pulse propulsion, laser-pushed light sails, or fusion rockets, all discussion of those missions will naturally use light years. A mission to Alpha Centauri, 4.24 light years away, immediately tells you that light speed travel would take 4.24 years. The travel time and distance have obvious connections. At 10% of light speed, which might be achievable, with advanced propulsion, the trip would take 42 years. At 20% of light speed, 21 years. These calculations are straightforward when using light years. With parsecs, you'd need to do conversions to understand timescales. Alpha Centauri at 1.3 parsecs requires mentally converting to light years before you can assess travel times at various speeds. The extra step adds friction without adding information. This creates pressure for astronomers to at least provide light years alongside parsecs in any context where the information might reach public audiences or where travel time might be relevant. Scientific papers about nearby exoplanets often include both units now. Press releases from observatories always do. The dual reporting has become standard practice when communicating beyond the professional astronomy community. The Parsec remains dominant in technical work, but light years serve as the public interface. And as long as space travel remains theoretical, this division works well enough. But if we ever develop the technology for actual interstellar missions, the discourse around those missions will be in light years, because that's the unit that makes planning and timescales intuitive. The parsec might remain the unit for cataloging stellar distances, but light years would become the unit for discussing destinations. Astronomy is becoming increasingly data-driven and interdisciplinary. Modern surveys produce datasets so large that individual astronomers can't analyze them alone. Collaborations span many fields, bringing together experts in physics, statistics, computer science, machine learning, and domain-specific areas. This creates friction when specialized astronomical units encounter researchers from other fields who think in different systems. Gravitational wave astronomy provides a perfect example, one of the most exciting developments of the past decade. The LIGO and Virgo detectors measure ripples in spacetime caused by colliding black holes or neutron stars. These detectors are sensitive enough to measure spacetime distortions smaller than the width of a proton. When black holes collide billions of parsecs away, the gravitational waves that reach Earth compress and stretch space by about 1 part in 10 to the 21st power. That's 1 part in a billion trillion. Detecting this requires the most precise measurements in the history of experimental physics. This field brings together observational astronomers who study the electromagnetic counterparts of gravitational wave events, theoretical physicists who model the gravitational wave signals using general relativity, experimental physicists who operate the detectors, and computer scientists running massive data analysis algorithms searching for signals in noisy data. Theoretical physicists modeling the gravitational wave signals work in SI units because the equations of general relativity are naturally expressed in meters and seconds. Their numerical simulations track black holes orbiting and merging, outputting gravitational wave amplitudes as functions of time. These calculations give distances in meters from the observed wave amplitude and frequency. But astronomers analyzing the host galaxies and electromagnetic counterparts expect distances in megaparsecs. When a neutron star merger produces both gravitational waves and a gamma-ray burst, astronomers want to know what galaxy it occurred in and how far away that galaxy is. They think in megaparsecs because that's what their galaxy catalogs use. Computer scientists building the data processing pipelines need to convert back and forth constantly. Gravitational wave amplitude gives distance in meters. Convert to megaparsecs for astronomical context. Galaxy redshift gives distance in megaparsecs. Convert to meters for gravitational wave analysis. Every conversion is a potential source of errors. The LIGO collaboration has developed careful protocols and extensive error checking to prevent unit conversion mistakes. But the friction is real, and it slows down analysis and creates opportunities for mistakes. Similar issues arise when astronomers collaborate with climate scientists. If climate scientists want to use astronomical data to understand solar variability's effects on Earth's climate over geological timescales, they shouldn't need to learn specialized astronomical units first. The data should be accessible in familiar units. If geologists want to compare impact crater ages to supernova rates that might have caused extinction events, converting between parsecs and familiar distance units shouldn't be a barrier to entry, but currently it is. A geologist trying to read astronomical papers about nearby supernova rates will encounter distances in parsecs and need to either learn the unit or constantly convert to something familiar. This creates an unnecessary barrier to interdisciplinary research. The knowledge should be accessible, but the specialized language makes it harder. The open science movement emphasizes making data accessible beyond the immediate research community that generated it. Data should be fair, findable, accessible, interoperable, and reusable. Requiring specialized unit knowledge to interpret data works against these goals. Parsecs are a barrier to interdisciplinary research, even if a small one. A physicist wanting to use astronomical distance measurements in their work has to learn what a parsec is, how it relates to meters, and how to convert. An engineer designing spacecraft trajectories has to deal with astronomical units and parsecs, even though their calculations use meters. A biologist studying the probability of life in the galaxy needs to understand stellar distances to estimate how many potentially habitable planets exist within a certain range. Do they need to learn parsecs to access this information? Currently, yes, if they want to read the primary literature. Some argue that learning specialized units is just part of interdisciplinary work. If you want to work across fields, you need to learn the language and conventions of those fields. Astronomers who work with biologists learn biological terminology. Biologists who work with astronomers should learn astronomical units. There's some merit to this argument. Specialized knowledge and shared conventions help communities communicate efficiently. Not everything should be dumbed down to the lowest common denominator. But there's a difference between specialized knowledge that encodes important concepts and specialized knowledge that's purely historical accident. Understanding what a parsec is requires understanding parallax, which is genuinely important astronomy. But once you understand parallax, there's no additional insight in using parsecs versus light years versus meters. The choice is arbitrary. The open science movement argues for reducing arbitrary barriers to accessibility. If the barrier served an important purpose, fine. But if it's just historical momentum, why maintain it? This creates pressure for better software infrastructure that handles unit conversion automatically. Instead of expecting everyone to learn parsecs, provide interfaces that present data in whatever units the user prefers. The astronomer can work in parsecs, the physicist in meters, the general public in light years, and software handles the translation. This approach respects the astronomical community's preference for parsecs while reducing barriers for others. It's a compromise that might satisfy everyone. The technology exists. Modern databases can store metadata about units. Modern software can convert between units automatically. Modern web interfaces can offer unit preferences. What's lacking is coordinated implementation across the field. Individual projects implement unit conversion, but there's no universal standard. Different databases handle it differently. Different analysis tools have different capabilities. The result is inconsistent and confusing. The International Virtual Observatory Alliance is working on standards for this, trying to create protocols that all astronomical databases can follow. If successful, this would make astronomical data much more accessible to researchers from other fields. But standardization is slow. Getting hundreds of different projects to adopt common protocols takes years or decades, and some resistance comes from astronomers who prefer the current system and don't see the problem. The future likely holds some mix of continued parsec dominance in professional astronomy, with better software infrastructure, making the choice less constraining for others. The parsec won't go away, but it will become more transparent, more easily convertible, less of a barrier. Whether that's the optimal outcome or just a compromise that satisfies no one completely remains to be seen. Teaching the parsec to students presents its own set of challenges that perpetuate the unit's use despite its unintuitive nature. To understand what a parsec is and why it's defined the way it is, students need to grasp several prerequisite concepts. They need to understand arcseconds as angular measurements, which requires understanding degrees and how we subdivide them. They need to understand astronomical units and how we measure solar system distances. They need to grasp parallax geometry and basic trigonometry. For a student taking an introductory astronomy course, to fulfill a general education requirement, this is a substantial time investment. These students often struggle with spatial reasoning and visualizing geometric relationships, drawing triangles with Earth's orbit as the base and distant stars, as vertices, doesn't come naturally to everyone. The concept of measuring tiny angular shifts and converting those to distances requires mathematical sophistication that not all students bring to an introductory course. That class time could instead cover topics students might find more immediately engaging and memorable: exoplanets and the search for life beyond Earth, black holes and what happens when you fall into one, the Big Bang and how we know the universe had a beginning, stellar evolution and why the sun will eventually become a red giant. These topics don't require understanding specialized distance units. A student can learn about the discovery of planets around other stars without needing to know those stars' distances in parsecs versus light years. Light years are far more accessible for teaching. Students already understand what a year is. They know light is fast, the fastest thing in the universe. The concept of distance light travels in a year makes immediate intuitive sense. You can teach the scale of the universe using light years without needing extensive mathematical prerequisites. Say, Alpha Centauri is 4.2 light years away, and students instantly grasp that it's far and that we're seeing it as it was 4 years ago. No geometric diagrams needed. But here's the educational dilemma. As long as professional research papers use parsecs, students planning careers in astronomy must learn them. They need to read research papers as undergraduates to prepare for graduate school. Those papers will report distances in parsecs or kiloparsecs or megaparsecs. The students need to understand what those numbers mean and how to work with them fluently. They need to develop intuition for whether a claimed distance makes sense given other properties of an object. So, introductory astronomy courses end up teaching both units, light years for the general education students who won't continue in the field, parsecs for the majors, and anyone planning to read professional astronomy literature. This dual instruction takes more time than teaching just one unit would require. It's inefficient but necessary given the professional popular split in unit preference. Upper level undergraduate courses and graduate courses teach exclusively in parsecs because that's what students will encounter in research. Every catalog they consult, every paper they read, every talk they attend at conferences will use parsecs. Learning to think in parsecs becomes part of professional socialization, joining the community of astronomers. This is true for any specialized field. Medical students learn to think in terms that seem strange to outsiders. Engineers learn specialized units and conventions. Lawyers learn legal terminology. Each profession has its initiation, rituals, its specialized knowledge that marks insiders from outsiders. For astronomy, the parsec is part of that initiation. Professors teach parsecs because they learned parsecs. They internalized the unit, developed intuition, for it came to think naturally in those terms during their own training. So they teach parsecs to their students who become the next generation of professors teaching parsecs to their students. The cycle continues independently of whether parsecs are objectively the best choice. They're what the profession uses, so they're what gets taught. And because they're what gets taught, they remain what the profession uses. This creates a self-reinforcing loop. Each generation inherits the infrastructure built by the previous generation. That infrastructure assumes parsecs. Databases use parsecs. Software expects parsecs. Formulas are written with parsecs. Young astronomers entering the field in 2025 learn to use this infrastructure. They don't question whether parsecs are optimal because the tools they need to do their work assume parsecs. Switching would mean abandoning or rewriting those tools, which is far more work than just learning to think in parsecs. By the time these young astronomers become senior researchers leading their own projects in 2045, they'll have 20 years of experience thinking in parsecs. They'll have developed deep intuition for the unit. A distance of 300 megaparsecs will mean something specific to them, immediately evoking a sense of scale and context. If someone suggests switching to a different unit, these now senior astronomers will resist, not out of stubbornness, but because their intuitions are built around parsecs. They'd have to rebuild those intuitions from scratch in a new unit. And what would be the benefit? So they'll design the next generation of observatories using parsecs. They'll write the data processing pipelines in parsecs. They'll train the next generation of students in parsecs. And the cycle continues. This isn't unique to astronomy. Every field has conventions that persist because each generation inherits them from the previous one and passes them to the next. The QWERTY keyboard layout was designed in the 1870s to prevent mechanical typewriters from jamming. Modern keyboards don't have this problem, but we still use QWERTY because everyone learned to type on QWERTY keyboards. Alternative layouts, like Dvorak, might be more efficient, but switching would require everyone to relearn typing. The cost is high and individual, while the benefit is uncertain and collective. So, QWERTY persists. Railroad gauge the distance between rails is 4 feet 8.5 inches in most of the world. This odd measurement comes from the width of Roman chariots, which determined the width of wagon wheel ruts in ancient roads, which influenced early railroad builders. It's completely arbitrary, but changing it now would require rebuilding millions of miles of track. Legal systems carry precedence from cases decided centuries ago under different social conditions. Academic institutions maintain tenure systems and departmental structures reflecting 19th century university organization. Every time we use month names derived from Roman gods and emperors, we're carrying forward arbitrary choices from 2,000 years ago. The Parsec is astronomy's version of this pattern, an arbitrary choice made for good practical reasons in a specific historical context, persisting because the cost of change grows higher every year as more infrastructure accumulates around it. Students entering astronomy today inherit a system built over nearly 2 centuries. They'll maintain that system extended and eventually pass it to the next generation. The Parsec will still be dominant in 2075 for the same reason it's dominant in 2025, because it was dominant in 1975 and 1925 and 1875, not because it's optimal by any objective measure, but because it's entrenched, and entrenchment is self-reinforcing. The Parsec story reveals something profound about how science actually works beyond the idealized version taught in textbooks. Science textbooks often present a narrative of pure rationality. Scientists observe nature form hypotheses, test them experimentally, and adopt the theories that best fit the evidence. Better theories replace worse theories. More accurate measurements replace less accurate ones. The field progresses inexorably toward truth. This narrative isn't wrong exactly. Science does progress. Our understanding of the universe is far better now than it was 200 years ago. We can measure distances to galaxies billions of light years away with reasonable accuracy. We understand stellar evolution, cosmic expansion, the formation of planetary systems. But the Parsec story shows that progress isn't just about logic and evidence. It's also about human choices, social dynamics, accumulated infrastructure, and historical momentum. The Parsec emerged from Friedrich Wilhelm Bessel's parallax measurements in 1838. It proved immediately useful for parallax work because of its geometric simplicity and direct relationship to measured angles. So far, so rational. Adopting a useful convention makes sense. But once adopted, the Parsec became entrenched through mechanisms that have nothing to do with whether it's the optimal unit by any objective measure. It became entrenched because changing requires coordinated action across a large community. Because databases accumulate that assume the unit. Because software gets written expecting the unit. Because students learn the unit and internalize it. These are social and institutional factors, not scientific ones. Yet they determine scientific practice as much as any logical argument about which unit is best. This is important to understand because it affects how we think about scientific progress and change. When we read that scientists disagree about something, we often assume it's because the evidence is ambiguous or the theory is uncertain. Sometimes that's true, but sometimes scientists disagree because they're embedded in different communities with different conventions and assumptions. The Parsec versus light-year divide isn't about evidence. Both units describe the same distances with equal validity. The choice between them is about audience context and community membership. Professional astronomers use parsecs. Popular science uses light years. Same distances, different conventions. Understanding this makes us more sophisticated consumers of science. When different fields use different approaches to the same problem, it's not necessarily because one is right and the other wrong. It might be because conventions differ across communities, standards vary between fields, or definitions aren't universal across all contexts. This doesn't mean science is arbitrary or unreliable. The distances are real, the measurements are accurate, the physics is sound. But the language we use to describe those measurements, the conventions we adopt to communicate them, the units we choose to express them, these are human choices, not physical facts. And human choices are influenced by history, by social dynamics, by institutional inertia, by the accumulated weight of existing infrastructure. These factors matter as much as pure logic in determining how science gets done. The Parsec also illustrates a broader principle about standards and change. Good enough beats optimal when switching costs are high. The Parsec isn't the most intuitive unit. It isn't the easiest to explain to non-specialists. It isn't the most natural for thinking about travel times or connecting to everyday experience. But it's good enough. It works. Astronomers can use it effectively. It connects to their measurement techniques. And the cost of switching to something better, rewriting databases, updating software, revising textbooks, retraining intuitions is enormous. So the Parsec persists, not because it's optimal, but because it's adequate, and the cost of change exceeds the uncertain benefit. This pattern appears everywhere. Technologies, institutions, languages, legal systems all carry forward historical choices that might not be optimal, but are good enough and too costly to change. This isn't a failure of rationality. It's a rational response to the reality of switching costs and coordination problems. Sometimes maintaining a suboptimal standard is better than enduring the disruption of change. The Parsec's story is ultimately about how arbitrary choices made for good reasons in particular contexts can become entrenched standards that shape practice for centuries. How social factors matter as much as technical factors in determining scientific practice. How history matters, decisions made in 1838 still shape astronomy in 2025. But here's the thing. Despite all this complexity about units and conventions and social dynamics, the fundamental wonder remains unchanged. When you look up at the night sky on a clear evening, those stars are separated by vast distances. Whether we measure those distances in parsecs, or light years or meters, or some future unit we haven't invented yet, the stars are still out there. Their light has still traveled across the cosmos to reach us, and that remains profound and worthy of wonder. Proxima Centauri sits 1.302 parsecs away, or 4.24 light years, or 40 trillion kilometers, or 268,000 astronomical units. Different numbers, same star, same distance, same light that left its surface 4 years ago, now entering your eye. The choice of units is a human decision. The distance is a physical fact. We can debate endlessly about which unit is best for which purpose, which convention makes most sense for which audience. These are legitimate questions worth discussing, but they're secondary to the deeper truth. We live in a vast universe. We've learned to measure it. We've built instruments that can detect the parallax of stars, thousands of light years away, precise enough to measure angles smaller than the width of a human hair seen from across a city. We've extended those measurements to galaxies billions of light years away, mapping the large-scale structure of the cosmos. We've measured the expansion rate of the universe itself. We've looked back in time to within a few 100,000 years of the Big Bang. These are extraordinary achievements of human curiosity, ingenuity, and persistence. The story begins with Friedrich Wilhelm Bessel, a self-taught accountant turned astronomer, standing in a cold German observatory night after night for 13 months, making measurements at the very edge of what 1838 technology could achieve. It continues through Henrietta Leavitt, an underpaid woman working as a computer at Harvard, discovering a relationship that would let us measure distances to galaxies millions of light years away, through Edwin Hubble, discovering that the universe is expanding, through thousands of astronomers building the cosmic distance ladder, rung by rung, technique by technique, and it extends to the future, to observatories being built now that will map billions of stars with unprecedented precision, to discoveries yet to be made about the nature and scale of the cosmos. The Parsec is part of that story. Not the most important part, not the most interesting part, but part of it nonetheless. A reminder that science is done by humans, embedded in history, shaped by social dynamics, influenced by practical considerations, but also a reminder that despite all the human complexity, the universe is out there, vast and beautiful and knowable. We can measure it. We can understand it. We can look up at the stars and know how far away they are, how fast they're moving, what they're made of, how they were born, and how they'll die. That's the real wonder. Not the units we use to describe it, but the fact that we can describe it at all. Good night.